Hello all. The first question from module 3 is define avial tree and explain the types of rotation in avial tree. Avial means the scientist name, that is G. M. Adelson Waleski and E. M. Landis. Definition of avial tree is avial tree is a binary search tree in which balance factor of every node, which is defined as difference between height of nodes left and right subtree, is either 0 or 1 or minus 1. If the balance factor is 0, plus 1 or minus 1, then the tree is called as avial tree. Otherwise, it is not a avial tree. In the example, this is the leaf node, hence balance factor is 0. Here also leaf node, 0 balance factor, and right minus left, that is 1 minus 0 is 1 balance factor for 4. For 7 there is no left, so 0 minus 1 is minus 1. For 5, 2 minus 2, that is 0 balance factor. For 20, 1 minus 0, that is 0 balance factor. For 10, it is 1, 2, 3 minus 1, 2. 3 minus 2 is 1. Every node has balance factor either 0, 1 or minus 1. So this tree is called as avial tree. And this is another example. Here leaf node is balance factor is 0, and for 4 balance factor is 1 minus 0, that is 1. For 7 is no left child, so 0 minus 1, that is minus 1. For 5 it is 2 minus 2, 0. For 10 it is 3 minus 1, that is 2. For 10 balance factor is 2, hence this tree is not a avial tree. Okay, that is the question answer for definition of avial tree. Next, types of rotation in avial tree. There are major 4 type of rotation. A rotation in an avial tree is a local transformation of its subtree rooted at node whose balance become 2 or minus 2. If the balance factor become 2 or minus 2, then we have to convert this tree into avial tree by 4 type of rotation, that is right rotation, left rotation, or left right rotation, or right left rotation. First type is single right rotation, where we rotate the node which is at balance factor 1 in clockwise position. Okay, and we apply this single right rotation is performed after new key is inserted into left subtree of left child. When the node is inserted at left subtree of left child, here we insert 1 at which position? At the left child of the left subtree. Here it is a left subtree and 1 is a left child, and we find the balance factor. Here is 0, 1 and it is 2, right? Next we rotate from here clockwise, that is 3 is rotated in the right position of 2, that is single right rotation. It is the first type of rotation, and 2 is present here, and we rotated 3 in a clockwise position, and 3 comes here, 1 comes here. Now find the balance factor. Here 0, here 0, and here it 1 minus 1, it is 0. Now it become avial tree. The second type is single left rotation. We rotate anti-clockwise. It is performed after new key inserted into right subtree of child of tree whose root had balance of minus 1 before insertion. We perform single left rotation when the new key is inserted into right subtree of the right child. Here 3 is inserted into right side, right subtree, and it is a right child. Fine. Then we apply single left rotation. First we find the balance factor of 3, that is 0, and for 2 it is 1 minus 0 minus 1, that is minus 1, and for 1 it is 0 minus 2, that is minus 2. And where balance factor is minus 1, we rotate into left side anti-clockwise, then hold the 2 here and rotate this one in anti-clockwise position. Then it becomes 2, 1, 3. And find again the balance factor for this 0. Here also 0, 1 minus 1, that is 0, and it also becomes avial tree. The third type is left right rotation, where we perform left rotation and right rotation. It is a combination of left rotation of left subtree followed by right rotation of new rooted tree, performed after new key inserted into right subtree of left child whose root had become plus 1 before insertion. We apply left right rotation when the new key inserted into left child and it is a right child, left subtree and right child. Here 2 is inserted in the left position of 3 and right position of 1. Then we apply left right rotation. First we need what is left right. First we perform the left rotation, that is 3, 1 and 2 is present, and we perform left rotation, that is anti-clockwise, and 1 is rotated, 2 comes here, 1 comes next to the 2, that become 3 2 1. We performed left rotation and we have to perform right rotation, that is clockwise. We rotate 3 in clockwise fashion, that is become 2 1 3. The fourth type is double right left rotation, which is opposite mirror image of double LR rotation and is left or exercise. That is double right left rotation means first we perform right rotation, then we have to perform left rotation. Find the balance factor first. This is 0, this is 1 minus 0 1, and for this is 0 minus 2, that is minus 2. First we apply right rotation, that is clockwise rotation. Here it rotates into clockwise, that become 1 2 and 3 goes down, 1 2 3. Okay, next it perform left rotation, that is anti-clockwise. We rotate 1 and 1 comes after left child, that is become 2 1 3. The second question is what is heap, and explain the properties of heap with the array representation. Then the definition of heap is a binary tree with the keys assigned to its nodes. It is nothing but a binary tree where we assign nodes, and it must follow two conditions to become a heap. It requires tree shape requirement and parental dominance requirement. What is shape requirement? It is essentially a complete, all its levels are full except last level where only one rightmost leaves may be missing. Then the second one is parental dominance, where the key at each node is greater than or equal to the keys at its children. Always the parent is greater than the children nodes. Okay, let's see this condition for some trees. It is an example 10 5 7 4 2 1. First we need to check tree shape requirement. It is a complete binary tree. Yes. Then a right child is missing. It may be possible because it is a shape requirement. Rightmost may be missing but leftmost is present, and it satisfies the shape requirement. And check for parent dominance. 7 is greater than 1, 5 is greater than 4 and 2, and 10 is greater than 5 and 7. It also satisfies the parental dominance, hence it is an example of heap. And see the second example. First check for shape requirement. Here left child is missing, and here right child missing is okay, but here there is no left child. Tree shape requirement fails because there is no left child and it is not a heap. See another example 9 5 7 4 6 2 1. Here is right child missing. Okay, it satisfies the shape requirement or because all the left child is there and it is a complete binary tree. And go for second condition, that is parental dominance. 7 is greater than 1 but 5 is lesser than 6. It fails to second condition, hence it is not a heap. There are four properties of heap, that there exists exactly one essentially complete binary tree with the n nodes. A tree is must be complete binary tree with the n number of nodes, and the root of the heap always contain largest element, that is a parental dominance property. And node of heap considered with all its descendant is also heap. If a node is considered with all its descendant is also heap, then it is implemented as an array recording element in top down left to right fashion. Consider it is a tree. We represent in array from top to down and left to right position. If 20 is inserted, then 14, then go to right 17, again go to 8 6 9 7 2 4 1 is represented. Convenient to store heaps element in position 1 through n of such an array. Levels of h of 0 is unused, that is h of 0 is unused, and we start to fill from index 1. Okay, next parental node key will be in first n by 2 position of the array, while the leaf keys occupy the last n by 2 position. Consider this is an array consisting of 10 element. They said that n by 2 position, that is 10 by 2, that is 5. 5 up to 5 it is of parental nodes, and leaf node occupy the last n by 2. After n by 2, that is a leaf nodes. We can see in the diagram also the leaf node are 9 7 2 4 1, that is 9 7 2 4 1. The children of a key in array's parent position I will be in position 2i and 2i position I plus 1 position, that is 20 is present in the 10th position, 20 is present in index 1. Fine. Then its children is in 2i and 2i 1 plus 2i plus 1 position. that is 20 is at one position, 2i means 2 into 1 in second position, and 2i plus 1 that is third position. It consists its children's. Parent of key in position will be in position I by 2. We have to find any node's parent, then we have to search for I by 2. If I need to find the parent of 10, that is I is 10, then 10 by 2 is 5. Whether element 1's parent is present in 10 by 2, that is 5, 6. Yes, 1's parent is 6. And we use I by 2 to check the parent. Okay, parent I returns I by 2, and if we want to check left child, return 2i, and if we want to check right child, then it is return 2i plus 1. And heap of I is always greater than maximum of heap of left child and right child for all I equal to 1 to n by 2. Consider here, let's check this. Parent is 20, which is in the position h of 1, and left child is 2i, that is 2 into 1 2, that is 14, and right child is 2i plus 1, that is a heap of 3, that is 17. And parent of 6, we have to find the parent of 6 by I by 2, 5 by 2, that is 2, heap of 2, 14. 14 is a parent of 6, and also parent of 4 is heap of 9 by 2, that is a heap of 2 4s. Heap of 4 is 8. Whether 4's parent is 8? Yes. And this is the 4 properties of heap. Third question is, for the list 297658, build a bottom up heap. To construct any bottom up heap, we follow build an essentially complete binary tree by inserting n keys in given order. If the given array, we first construct a complete binary tree in a given order itself. The second condition is heapify a series of tree. Exchange its key with the key of its larger child and heapify the subtree. This is the rules to follow the bottom up heap construction. Let's see this example 297658. Here the number of element n is 6. Fine. Then we have to find how many parents and children are there. N is 6. 6 by 2 is 3. Up to 3 index there are parent, and after that there are, this is the parent and this is the leaf node. First we construct complete binary tree in a given order, that is 2 9 7 6 5 8. Fine. Then in this array we have to see the last parent, last rightmost, starting with last rightmost parental node. Fine. That is 7. Compare the 7 with its children, that is 8. Of course 8 is larger, hence we heapify with 8. 8 9 2 9 6 5. Here we swap this element. 7 is done. Next element is 9, right? Next compare 9 with its children. Compare 9 with its children, that is 6 and 5. 9 is already greater than 6 and 5. There is no swap required. 9 is also complete. Next go for 2. Compare 2 with its children, that is 9 and 8. Again here 9 is greater than 2. Swap 9 and 2. 9 2 8 6 5 7. Okay. Again go for here. Here we completed first iteration, that is 9 2 8 6 5 7. Okay. Next here it is parent, it is children. Start again, compare 8. 8 is already heapified, it is done. Next is go for 2. Compare 2 with its children. Okay. 2's here 6 is greater than 2. Swap the element and we finally get this as 9 6 8 2 5 7. Another example for constructing bottom up heap, that is 1865374. First n is 7 and parent is 7 by 2, that is 3. Up to index 3 there are parent node, and after that there are leaf node. Construct first a complete binary tree, that is 1865374. Next start to heapify the element. Start from 6. Compare 6 with its child, that is 7 and 4. Yeah, 7 is greater, swap this. It become 1876453. 6 is done and go for 8. Compare 8 with its children, that is 5 and 3. 5 and 3 are already smaller than 8, then no swap is required. 8 is done, then go for 1. Compare 1 with its children, that is 8 and 7. 8 is greater, swap at this position and it become 81753641 is also done. And we completed 817536 4. Now the parent is 8 1 7 and the children is 5 3 6 7. Again start to heapify. Check whether 7 is greater than its children. 7 6 4, it is already in order. Then go for 1, whether 1 compare with its children. Yes, 1 is smaller than 5 and 3. Swap the element 5 1 3. It's also done. Then compare 8 with children, that is 5 and 7. It is already heapified. Then the order is 8 5 7 1 3 6 4. It's also done. In time complexity, in the best case analysis, if heap is given, heap is already satisfy heap property with respect to children, then it is a best case, and efficiency is order of n because there is comparison is less than n, and time complexity is order of n. In average case, if the random array is given, then the efficiency is also order of n, comparison also order of n. In the worst case analysis, when the all the given array is sorted in a way such that subtree rooted at any violet heap property require maximum adjustment to construct a heap, then efficiency is order of n, then the comparison is less than 2 to the power n, that is similar to 2 into n minus log of n plus 1. And it is a derivation for time complexity in worst case analysis, how we are going to get 2 into n minus log 2n. Okay, then the number of comparison is required is 2 into height of minus 1. Height minus 1 becomes that is nothing but distance from level I to reach high to leave h. Okay, if we have node 5, height is 5, then we need 1 into 2 into 5 minus 0, that is 1 into 2, that is it is in the level 2. Like the way it goes on. In the worst case analysis, we come start from 2 into h minus I, that is for all the level keys, and for I 0 to h minus 1, and we derive this to get 2 into n minus log of n plus 1. And fourth question in module 3 is explain Horspool's algorithm, and they given a question by using this algorithm to solve a pattern matching. Horspool's algorithm is used for pattern matching, and it is used to find a substring in a given string. To find Horspool's algorithm, first we create an algorithm shift table. It is an algorithm to create a shift table that consists of a pattern 0 to m minus 1 and alphabetic character. M is the size of pattern. Okay, let's see this with example where we get clarity about this algorithm. And output is a table. We have to create a table of 0 to size minus 1 indexed by alphabetic character and filled with the shift size. For I 0 to size minus 1, table of I is filled with m, and for j 0 to m minus 2, the table is filled by m minus 1 minus j and return table. It is the first step in Horspool's algorithm to create a shift table. Let's see this algorithm with example. See the example, the pattern is Bengaluru in alphabets. Okay, the text is alphabet, that is a character A to Z. Fine. Then fill the table. What algorithm say? Fill the table I with the m, that is the size of pattern. M is nothing but size of pattern. Okay. Here Bengaluru have the size is n. There is n alphabet character. Create a table with the size of pattern. Okay, that is 9. First we create filled the table with 9. Okay, next the formula says that for j 0 to m minus 2, do table is pattern of j m minus 1 minus j. That is nothing but we have to find p of j, create another table called p of j where it is m minus 1 minus j. Okay, what is j here? The given pattern is Bengaluru. Start from 0, 1, 2, 3, 4, 5, 6, 7, 8. Fine. P of 0 is m minus 1. That is 9 minus 1 minus j is 0. That is 8. Replace where b is present. 9 is replaced by 8. Fine. Next is, and we also see the 8 manually. How big? How? That is, consider from b how many front words. That is 1, 2, 3, 4, 5, 6, 7, 8. There are total 8 words in front of B. So we get 8. And A 1, 2, 3, 4, 5, 6, 7, right? Okay. From A 1, 2, 3, 4, 5, 6, 7. That is 9 minus 1 minus 1. That is 7. 9 is replaced by 7. Where 9 is replaced by 7. Next n 1 2 3 4 5 6. Where is n? 9 is replaced by 6. For G again it is 1 2 3 4 5. G is replaced by 5. And for L 1 2 3. Well, 9 is replaced by 3. And for O it is 2. 9 is replaced by 2. Next for R it is 1. For R 9 is replaced by 1. Fine. And we need to know that is from here A 1 2 3 4. Initially A is 9, then it is replaced by 7, then it is replaced by 4. We need to consider the least possible here, that is 1 2 3 4. 4. We considered here 4. 8 5 3 6 2 1. It is a newly created table. This is how we create a shift table. Let's see another example to create. The pattern is VTU Belagavi. Okay, how many alphabet character is there? 1 2 3 4 5. Consider this underscores also. 1 2 3 4 5 6 7 8 9 10 11 12. Pattern consists of 12 characters. Replace all here by 12, and underscore is also present. Replace it as here underscore also consists to 12. Fine. Next we need to find distance from V to reach the last position, that is 1 2 3 4 5 6 7 8 9 10 11. Replace 12 by 11. And for T 1 2 3 4 5 6 7 8 9 10. For T 12 is replaced by 10. It is also fine whether if you apply, no need to check the last, you can apply m minus 1 minus j, or else you can see the till the last position. We can also see to find the shift table. Hope you got to know how to create the shift table. Then look at the Hospoole's algorithm. Pattern is 0 to m minus 1 and text is 0 to n minus 1. What the input they given? They given pattern and text. We need to find whether the given pattern is present in text or not. Okay. First we need to create a shift table. That's why we need to know the algorithm to create a shift table. Call shift table of pattern 0 to m minus 1 initially. Then from I m minus 1 while I less than n minus 1 do. K is initialized, that our new pattern table is initialized with 0. Then while K is less than size minus 1, and also pattern of m minus 1 minus K is equal to T into I minus K to K is incremented K into K plus 1. If K, the newly created table, is equal to m, then return I minus m plus 1, else return I into I plus table of text of I. Return minus 1. Let's see this how to apply this Hospoole's algorithm in a given question. We need to know 4 conditions before we are going to matching the pattern with the text. Consider the text is barber. Okay, it is a pattern is a barber, and the text they given something else. Here it is got exchanged. Okay, fine. Pattern is a barber, and they given some text consists of yes. In brute force approaches, we considered from the starting element and we goes on by considering the first element. But in Hospoole's algorithm, we need to check from last position. If the text consists yes, consider the text consists yes, and we need to consider the last letter R. R is matched with yes, no. R is not matched with yes. Then check whether yes is present in the given pattern. S is there? No. R is not matched with the last position in the text yes, and S is also not present in any of the pattern. So we move entire barber from the text's right position. Okay, it is the case 1. In the case 2, pattern consists B letter and the pattern barber. R is matched with B? No. Then check whether B is present in remaining. Yes, B is present here. Then we need to see the shift table and the value of B in the shift, that is we need to move B in the place of B. Fine. Then ER, then remaining value is here. It is the second condition. In this we entire move barber from this text. In this we matched B first, then we replaces the place. Okay. In the case 3, what happens? The last position is matched. Fine. Then the next position is also matched. But then after few condition gets true, then check for the next. K is matched here? No. Whether K is present any of this position? No. Then it is the same as this. We need to move entire barber from the text. Okay, it is the third case. And the fourth case, which is related as case 2, that is barber, and the text consists of R, E, R. Whether R is matched, E is matched, yes. Next, after 2 or 3 comparison, checks A. A is matched with B, B, no. But A is present here in the remaining, yes, A is present. Then move A here. A, B, A, B, E, R. This is the 4 condition you need to know before matching the pattern with the text. Given question is Jim saw me in a barber shop. Fine. The pattern is barber. First we need to create a shift table. The first table we need to check how many n, that is number of character here, that is 6. Write A B C D till Z, and the B, all the alphabetic character is replaced by 6. Fine. Then what we need to do, check B A B R B E R, create another one, check for B, P of 0 is 6 minus 1 minus index position is 0, that is 5. 1 2 3 4 5. Fine. B is 6 is replaced by 2. Next, for A, it is 6 minus 1, that is 4. 1 2 3 4. A is replaced by 4. Fine. Next, again R, that is 1 2 3. R is replaced by 3. Again B, 1 2. In the initial case, B is replaced by 5, but again here it is the closest is 2. B is replaced by 6 is replaced by 2. Again for E, that is 1. E is replaced by 1 and remaining is 6 here. We created a shift table. It is called as a shift table. Fine. And here it is the text and it is a pattern. Start to match R, last one R to A. Whether it is matched? No. Then whether A is present in the remaining text? Yes, A is present here. Then we need to shift A by how many position? We need to check the shift table. Fine. Where is the shift table? Here value of A is 4. We need to shift A by 4 position, that is 1 2 3 4. A comes here. Remaining is as it is. Again start comparison. R is compared with E, R, B, E, R. R is compared with E. Pattern is not matched. Then check whether E is present here. Yes, E is present here. Then we need to shift by how many value? 1 value. E is shifted by 1. B, A, R, B, E, R. Next again start matching whether R is matched with the underscore. No. Whether underscore is present in the pattern. No. Then we have to completely shift the barber. That is B, A. B, A, R, B, E, R. Again match B with the R. Whether it is matched? No. Then compare whether B is present here. B is present here. Shift by 2 position. B is shifted 1 to B is come here. B, A, R, B, E, R. Next B comes here, E is here, R is here. Okay, next match R is matched with R. It is matched. Next A, compare A with E, whether it is matched? No. Whether A is present in the text? Yes, it is here. Then we need to shift 4 position, right? Move A 1 2 3 4. Right. That is 1 2 3 4. A is moved by 4 position. Then again start comparison. R is matched with R, E is matched with E, B is matched with B, and R, A, B. This is barber. We get the pattern. This is another example which is not in the model question paper. Just for reference, this is a given text and the pattern is TCC, TA, TT, C, TT, which is a DNS pattern. M is 10 and create a shift table. Try to create it and try to match. And we got here TCC, TA, TT, C, TT. Try to do this, which is good example for Haas loop algorithm. Thank you.